All right, so I'm going to just recap a little bit of where we ended last week. Uh, so we basically were doing PD controller design, and in PD controller we added a zero to our system. Maybe I'll just go a little further back. And the idea of PD controller is that by adding a zero to our system, we're able to change the trajectory of our closed loop poles. So we're basically able to change the root locus, the shape of the root locus. And then by doing so, this allows us flexibility in moving our root locus to a new desired closed loop pole location. Usually that closed loop pole location is using second order approximation of what we want out of the performance. So when we move our system to a desired closed loop pole location, even though the system might be higher order, we are just going to use second order approximation as a starting point for our design. Once we pick our PD controller, we get our new root locus and our associated gain with it. But then you would test the system performance by using a step input in MATLAB to see how it responds. And usually when we look at this, we use some step info from MATLAB to just look at the settling time or whatever performance metrics we're trying to achieve. So we ended with a I showed you an example of like what a PD compensator in real life looks like. It's based off of a capacitor and resistor in series with a op amp. And basically how it's a derivative because the output voltage is proportional to the change in voltage. And then we're moving on to lead compensator design. For this week, we'll finish that today and we're gonna start PI controller design. So the lead compensator design is a passive network that adds a compensator pole and zero and reduces the transient response time. And from last week, the main takeaway with lead compensator is that you want your added pole to be more to the left than the zero. This is just an important criteria. So your zero is going to be close to the origin while your pole, or closer to the origin while your pole is further away from the origin. So then lead compensators are simpler to use due to no active power source. And since it's not a true derivative, you don't have to deal with the issue that PD controllers do, which is taking the derivative of something noisy will make that noise bigger. So lead compensators tend to avoid that. And the reason why we want our pole to be greater than our zero, or when I say greater in magnitude, it's because we want something called phase lead. So basically, the whole idea of lead compensator is that they reduce your system delay. PD controllers also do the same thing where they reduce your system delay as well. But in this case, for lead compensator to work well, you need your pole to be further away from your zero. So this is the main design criteria. If your P is not greater than Z, then if your P is, I'm sorry, if your P is greater than Z, you need to redesign this, if your P is greater than Z, you're good. But if your Z is greater than P, then you need to redesign the system again. So then, I talked briefly about the effects. It's similar to PD compensator where it improves your transient response time. There's less noise amplification than PD compensators, and it's a passive system, but it's not as effective as a PD compensator. And it's since we're adding both a pole and zero, there's added complexity to this design. Do we talk briefly about the design process? The main difference between this and the PD controller design is that we arbitrarily pick a pole location or a zero location, and then we use the angle criteria to then pick the complementing pole or zero to meet the angle magnitude criteria. And a little bit of it is luck for our pole to be greater than the zero. I'm not a huge fan of this design because you rely a little bit on luck. So one thing that the textbook really likes to do is they like to do pole zero cancellation, completely valid. If you want to do pole zero cancellation on your homework, that's completely valid. In my examples, I don't do pole zero cancellation to show you that we can still do it without pole zero cancellation. And even though it's a little bit harder, I think it's nicer to go over a harder homework example and then harder lecture example and then use pole zero cancellation to your advantage when you're actually doing your homework. And I encourage it for your homework. Now we started this example where we're designing a lead compensator such that system has less than 30% overshoot in a 2 times reduction in settling time. In the PD controller, we're able to keep it at 16% overshoot with a 3 times reduction in settling time, but because lead compensators are not as good as PD compensators, we have reduced the constraints. And then we found the desired closed loop pole location based off of the criteria of reducing the settling time by half. And when we were able to find that, paired with the percent overshoot, we're able to find the new desired closed loop pole location, which is indicated in purple here. One little recap, that diagonal lines like this, the green line is a constant damping ratio line. So lines that go off from the origin are constant damping ratios, and then constant radius about the origin is basically a constant natural frequency. So once we were able to figure that out, and we had our desired closed loop pole location, we want our root locus to pass through that point. So then we picked a 0 at -5. So that's where we arbitrarily picked that point. And then we're using the angle criteria to find the location of the closed loop of the pole, of the lead pole. And right now we're trying to figure that out. We don't know if it's between 0 and -4. I just put it there for visual reference and defined it as theta 4. So what we're doing now is we're finding theta 4. And once we find theta 4, we can then work backwards to find where -PC is to have that corresponding angle of theta 4 going to that point, -2.014 plus 5.252J. So we left off there. We found the angles theta 1, theta 2, and theta 3, which is our 3 poles. And then we found the angle of the 0 that we arbitrarily picked, which is at phi1. And from there, we're able to find our angle, which is 7.3 degrees. Main takeaway here is for the pole to be more further to the left than the 0. We want our angle of our 0 to be bigger and our pole to be smaller. And we indeed were able to conclude that 60.38 is bigger than 7.31. And you can just see on the graph that, angle like this is really small, meaning that this point is really far away compared to like the 0 right here. Like this is 7.3 degrees. That's 60 degrees. So we're good. So from that point on, what we have to do is we now have to find the pole location, and basically I guess what we do is we just say tan of 7.31 degrees is equal to, it's going to be the evaluated position, which is minus, it's 5.252 minus 0, because the pole is on the real axis. It doesn't have a height, divided by minus 2.014 minus PC, because minus PC is the actual pole location, because we use this form, C of S is equal to S plus ZC divided by S plus PC. So actually it's minus PC is the actual pole location. And from that, we're able to find out PC is going to be equal to 42.96. So now that we have that, we can see that the pole is much larger than the 0. So we have a phase lead system, meaning that this is a valid lead compensator design. So PC is greater than ZC. So this is a lead design. One trick I also like to, or not say trick, but one thing I noticed is that when your pole is going to, if you make your pole much larger in magnitude, so like if you pick -20 or -30, then your 0 is more likely going to be closer to the origin than your pole, so that will work as well. So I am going to add another page here because I'm out of space. But basically, now that we found our design, I'm going to call C of our lead design. We still need to determine the corresponding gain that gets us to that closed loop pole location. But for now, I'm going to write down our lead design, which is S plus 5 divided by S plus 42.96. And basically, we apply the magnitude criterion. Where K is equal to 1 over the magnitude of our open loop transfer function, evaluated at minus 2.014 plus 5.252J. So K is going to be equal to 1 over C of S, G of S, evaluated at that point. And we're going to get 1,423 as our gain. So then maybe I'll write out the whole system now. So the open loop transfer function is going to be 1,423 multiplied by S plus 5 divided by S plus 42.96 multiplied by one over S times S plus 4 times S plus 6. Okay, so I have in MATLAB coded up the lead compensator, and we can compare it to the PD compensator. Just a reminder, the settling time of the uncompensated system had a settling time of 3.97 seconds. And we're aiming for basically, we want 1.99 seconds or better and 30% overshoot. That's what we want. One other thing is that now that we have we have a pole at the origin, we have a pole at 42 point, we have a pole at 42.96 or minus 42.96. We have pull at -4, pull 0 at -5, and the pull at -6. So I know for sure that we have a pair of complex conjugate poles closest to the origin, but then we have a third pole between -5 and -6. And then we have a fourth pole beyond minus 42.96, meaning that because of our third pole between these 2 points, second order approximation will not hold. So this design is based off of second order approximation. So now we have to confirm if it's true or not by testing it. Okay, so here we have from the other day, we have our PD compensator, and we have where we had a system with under 16% overshoot. So now we have the same system, but now we're using the design criteria for a 30% overshoot, where we found that zeta is 0.358. And okay, well, I'll walk through each of the steps. All right, so what we do is first we're just going to create the uncompensated transfer function right here. So we now have to find the uncompensated transfer function. And this is the open loop transfer function. Then what we do is then we use root locus to find the point where the closed loop transfer function has 30% overshoot. And that's going to be around 63, and which is right there. So close enough. So there you can see we have 31.2% overshoot. So we choose the gain, corresponding gain at that point, which is 65.1. So I actually found that it was going to be 63.2. So then I create the closed loops transfer function here using that gain, and I use step info to get the uncompensated performance. So uncompensated performance tells me our settling time is 3.98 seconds, so we want half of that. And our actual overshoot is 28%. So this is using second order approximation. We actually found that it was 3.97. It's close enough to 3.98. So you divide that by 2 to get our new compensated settling time. And then from there, I was able to find our natural frequency and then our new desired closed loop pole location defined as PC. Now, in our calculation, we found that K lead equal to 1,423 was what we wanted for 30% overshoot and the selling time half of the uncompensated selling time. We added a pull and zero at -5, and we added a zero at -5 and the pull at -42.96. So then we multiply our C lead by our uncompensated system. Notice here I leave the gain out because um, we pull the gain out because if we don't do this by hand, we can actually calculate the gain we need. And I'll show you what I mean by that. It'll make more sense if I just show you. So let's say I found the desired closed loop pole in zero, but I haven't found the gain yet. I don't want to calculate the I don't want to calculate the magnitude criterion by hand. What I'm going to do is I'm going to basically determine the 30% overshoot with my dominant closed loop poles, which is roughly going to be 0.358 was the damping ratio. So we're going to go down to 0.358. There you go. So 1,420 is what MATLAB tells us. 1,423 is the exact value. And you can see that the percent overshoot is 30%. Well, sorry, that's a little bit small in the figure, but hopefully you'll be able to see that. Then what I was talking about is so we have our dominant poles roughly there and there, but then we have a third pole right here at 1,423 as well, around there. So that's our third pole, and then we actually have one more pole if I write around somewhere here, 1,423 is around here. So this system has 4 closed loop poles. Something like that. Anyway, so we're still using second order approximation. We hope it works. And if I run it and I check the step info of our compensated closed loop system, be sure to apply the gain here. Our new selling time is actually 1.96 seconds, um which is actually pretty close to our what we wanted. We wanted under 2 seconds, and it worked out well for us. Uh, our percent overshoot is a little bit high at 30.5%. So you typically, to reduce your percent overshoot, you reduce your gain. So if I were to say instead 1,400 is too high now, and we have a little bit of leeway with the transient or the selling time, we can reduce the gain. Usually increasing gain will improve your transient response, but it's at the cost of percent overshoot. It's a trade-off. So if I reduce it to 1,200, we can see our selling time actually improves a lot to 1.65, and our percent overshoot is much lower. So it works. We actually perform better by reducing the gain of the system. But I don't really mind. Let's say in the homework, you designed everything according to how I told you to do it. And when you go to the analysis portion and you find that your second order approximation didn't hold and it didn't meet your design specifications, that's fine. You can leave it like that. I will not penalize you. If you want to play around with the gain, you can, but you can just leave it as is. Any questions? Okay, very good. So that wraps up part one of our lecture. Sorry, I was a little late on uploading part two. Part two has been uploaded. Um, so we found that this works in MATLAB. So that's our final answer. So then here's a application of a Lie compensator. And the way we would design the poles and zeros or choose the poles and zeros is by choosing our resistor values, R1 and R2, and our capacitance value, which is C. And this is the transfer function given here. And this is how a Lie compensator would work in an analog electric system. And notice that there are no op amps, so you don't need active powers. And you can see that the resistors 1 and 2. Oh yeah, so and beta is where we have the second resistor in play there. So just some takeaways. PD and lead compensators' primary purpose is to improve the transient response and are not designed for improving the steady state error. However, steady state error may improve. I'll show you that in PID controller design. Um, One thing, the reason why steady state error may improve is because we're basically choosing a gain, and by choosing the gain, we're able to reduce the steady state error. Um, by increasing the gain, we reduce steady state error. Compensator design are based on first and second order approximation with the dominant poles. Mainly the textbook highlights second order approximation. I wouldn't really worry about first order approximation. Let's just stick with second order approximation. Uh, PD and Lie compensators reshape the root locus such that the dominant closed loop poles will reach our desired location. And PD compensators require power and may amplify noise because of the derivative operation. And then finally, Lie compensators are passive but do not perform as well as PD compensators. So that wraps up basically just up to chapter 9.3 or chapters 9.1 through 9.3. So then we're going to go on to design via root locus part 2, which is going to cover uh, PI compensator, lag compensator, which is section 9.2. And then finally, we're going to be talking about the total response using PID and lag lead compensator. So this is where we combine everything. Uh, this is also a long lecture. It's going to be 36 pages. Most likely for midterm 2, we'll probably just get to PI and lag compensators, and I don't think we'll be covering that on the exam. Okay, so PI compensators uh, are also ideal compensators or ideal controllers. The purpose of that is that we increase the system order. So in chapter 7, on steady state error, we introduced the idea of type 0, type 1, and type 2 systems. Uh, so type 0 systems are basically when there are zero open loop poles at the origin. So when you have a type 0 system, you have a steady state, you have a constant steady state error for a step input. If you have a ramp or parabolic input, it goes to infinity. For type 1 system, you have one open loop pole at the origin. That means you have a constant steady state error for ramp input, and you actually have zero steady state error for step input. And then when you have two open loop poles at the origin, you have a type 2 system, and that means you have a steady state error constant for parabolic input, and then zero steady state error for ramp or step input. So PI compensator increases the system type by 1 and will reduce the steady state error from constant to 0 or from infinity to constant. So if I have a type 0 system, a PI controller will make it have a 0 steady state error for step input and a constant steady state error for type 1 system. So yeah, so PI compensators increase the open loop system type by 1. And that's the takeaway. So the ideal, so PI stands for ideal integration compensation, or it's called proportional plus integral, and it uses error which is proportional and the integral of the error to feed into the plant. So we do that by adding a 0 and a pole. And it might sound similar to a lead compensator design, but it's actually quite different because the pole we add is at the origin, and the 0 we add is a pole very close to the origin. So when we work this out here, you can see that this is our integral portion. This is our integrator. When we multiply something in the S domain, it's the derivative. When we divide something by S in the frequency domain, it's an integrator. So this is our integrator part. And this is just our proportional part. So a proportional part still uses error as feedback, but then it also takes the the total area, like under the error function, as part of its feedback as well. So here let me put a period here for grammar. So we actually would rewrite this as K plus Ki for integrator over S, where Ki is equal to K times A. So PI controllers are actually really easy to use because, or at least calculate, because the purpose of a PI controller is to increase the system type, but not change the root locus. So when we add a 0 close to the pole, we actually maintain the shape of that root locus, more or less. So PI compensators generally do not affect the initial transient behavior. Um, Instead, so we increase the system type to reduce steady state error for standard test inputs. It requires active circuitry, meaning we need a power source for the pole at the origin. It's not designed for improving the transient response. If anything, it actually might make the transient response a little bit worse, and I'll talk about that more later. PI compensators may increase the settling time due to the dominant closed loop pole located between the added pole and 0 from the added pole and 0. And then adding a PI compensator will not alter the root locus shape significantly. So what I mean by, yeah. Or yeah, it might reduce error, but its primary purpose is to improve the transient response time. It will change the error though, because you're choosing a gain that and just by changing the gain, you change the steady state error constant value. Yeah, so exactly. So we add PD and PI because PI won't really change that, that peak you see. The time to get to that peak will more or less be similar. And then PD will then reduce that peak time. But it won't really fix it won't really fix the error part. PI comes in and will make the error go to zero or make an infinite error go to constant. That's the role of the PI. So the whole purpose of the PI compensator is to increase the system type by one. So when I talk about it not changing the shape of the root locus that much, if we look at a system, if we look at the root locus example with the security camera, where you have a pole at the origin and a pole at, I don't know, -2 or something like that. It looked kind of like this. Our root locus looked like that. Nah, actually, that's not a good example because I need a pole at. But we have something similar where we have a pole here and here. So the closed loop poles will approach towards each other, break off, and go to infinity at 90 degrees and -90 degrees. So we have infinite poles like right here, and infinite pole down here. And basically what we're doing now is we have the same thing now. And then for our PI compensator, we add a pole at the origin and a zero very close to it. So real axis segment tells us that there's going to be a pole between these 2 points. And we still have a real segment here between these 2 points because we have an odd number of poles and zeros to the right of the red lines. And we'll still have a breakaway point. It might look a little bit like this now. And our asymptote location is going to be slightly different because of these added poles and zeros. But it won't change that much because they're close to each other. Because the asymptote is going to be equal to the sum of the zero or sum of the poles minus the sum of the zeros divided by the number of poles minus the number of zeros. Um, this barely moves the asymptote because they're so close to each other. Because when you add the location of these two together, they're a very small number. And then the asymptote angle still remains the same. So the root locus will be slightly different, but they're roughly equal to each other. So that's what a PI compensator does. It does not affect the root locus shape significantly, but it does increase the system type. So by doing that, we reduce our steady state error to 0 or constant for standard test inputs. It requires active networks and may increase your transient time. I'll talk more about how it does that with that because by having this here, we now have a closed loop pole really close to the origin, which makes it have a very slow transient response time, but it's not that big of a deal. And I'll show you why with an example later. So steps for PI compensator design is very easy. All you gotta do is you have to place a pole at the origin, and then you pick a zero close to the origin in the left half plane, and then we simulate that response, and then we adjust the zero location accordingly if our transient response time is too slow. So note that the further the zero is from the pole at the origin, the more the root locus shape will change, which we do want to avoid for PID compensator design. So if the transient response time is slow, we would then make up for that slowness with by designing a good PD controller. Okay, so what we're going to do here is we're going to find the steady state error for the system where the closed loop system has a damping ratio of 0.174 and with C equal to 1. This just means it's uncompensated. Then we're going to design a compensator for PI compensator where the closed loop system still has the same damping ratio, but now zero steady state error. Okay, before we even start this, let's just look at I didn't give you metrics for like for step or ramp input. You have to figure that out right now. Uh, we only add a PI controller when we want to make the steady state error 0 or constant. And here we're asking for the system, the final system to have a 0 steady state error, meaning that we're increasing the system type by 1. If we look at the system, this is a type 0 system. So we know that there's a steady state error. ESS is constant for a step input. So we're going to be applying the steady state error for step input where basically ESS is going to be equal to 1 over 1 plus KP, which is our constant from chapter 7, where KPU of our, so this is our uncompensated constant, is limit as S goes to 0 of K times G of S. So the K is assuming that we can pull a K out here, maybe a K block right here where we can adjust the gain K. So in from MATLAB, we found that K is equal to 163. This is from MATLAB. Found that K is equal to 163, which corresponds with damping ratio 0.174. And we get 163 over 20. And then we apply that to our ESS equation. Is equal to 1 over 1 plus 163 over 20, which is equal to 0.109 or 0.109. Yeah. All right. Right. So then if we do a step input, we'll find that our final value is going to be equal to our step input at infinity minus our error at infinity. So I got that from here where E of S is equal to Y of S minus U of S. Take the final value theorem, you can find that Y is equal to man, no, I flipped it. U of S minus Y of S. So then when I take the final value theorem and I rearrange it, we find that steady state value of Y is equal to the steady state value of U minus our steady state error. And for step input, that's going to be 1 minus 0.109, which is equal to 0.891. Okay, so at this point, the next two steps I'm going to do on the computer, but I'm going to write them out here. So I'm just going to place a pole at the origin. We just choose, add a PI controller. And C of S is equal to K times S plus ZC over S. And we'll just put 0 arbitrarily close to it. Let me see what I did in MATLAB. So I chose a 0.2. All right. So we choose K is equal to K times S plus 0.2 divided by S. And then we choose our K compensated system that corresponds to K that corresponds to zeta is equal to 0.174. That's it, and we're done. You don't need to calculate anything. It's just MATLAB now or Python.
So what was the step? Like us finding the steady state error?
Yeah.
What did they even do?
It's just to confirm that what we see in MATLAB, or yeah, you don't really need to do this, but we just needed this because that's what the example asked for. But this is just it's like a sanity check. When I do a step input, I just want to make sure that I'm converging to 0.891. I had it in my notes. To be honest, that's the main reason why I wrote that down. It's just because it was in my notes and I wasn't sure what I was thinking last year. But if I were me a year ago was probably doing this as a sanity check. So let me swap screens again. So we're back to MATLAB. And I think maybe if I'm here next year, I'll probably do this in Python instead. That's why I say every year. Okay, so first we just check our uncompensated system. Oh man, I did not define things properly. Unrecognized function GU. Let's clear that. Okay, run the section. All right. And we found that 163 was the value using our locus. So I found it in that step. So I had to run it, place the root locus. And oh well, spoilers. Anyway, so I added a 0 at minus 0.2, a pole at the origin. So then this is the step I'm talking about where basically what I'm doing is I have that, and actually let me show you these two. So to the left of this figure and to the right are two different systems. Oh, so I'm sorry. I just keep messing things up today. All right, to the left of this is the uncompensated system. To the right of this figure, it's the compensated system. Now it has the PI controller. If you look at them, they look pretty identical. And if I were to zoom in, you might start to see some differences only when I get very close. So mainly it's when I get to the origin. I mean, you can see that there's a pole 0 right there. And it's going to affect the root locus shape just a little bit. And we're looking for 0.174 damping ratio, which is going to be around there. And you'll see that the 0.174 is perfect. Has a pole at minus 0.66. If I try to find that same point here, actually, I need to zoom out a little bit. And let's go to this point. Point 174. All right. All right, cool. You can see that our gains are slightly different at 152 compared to 164. Even the pole location is a little bit different. It's a little bit shorter. at 3.74 compared to 3.92. Notice that the natural frequency is also different. So while adding this pole and zero close to each other does increase the system type, it does change the closed loop pole location a little bit, even though the overall shape is more or less preserved. So I chose 158 based off of that. Was it? Yeah, it was probably 158 or 152, whatever. Yeah, 152. Let's change it to 152. 152 is what we chose. I'm gonna run that section. And then uh here's a comparison of the uncompensated and the compensated system. 0.89 was the final value for the uncompensated system, which we can probably see right here. Or not. Guess I can't click it. And you can see the compensated system is converging to 1. Now, the reason why the transient response time takes a hit is because of that closed loop pole added close to the origin. Okay, so I'm going to wrap this up. So because of this closed loop pole added close to the origin, this decay is really slow. So what we're seeing here on this final plot here is that we're seeing this very slow decay to the final value of 1. So you can see here, though, that both systems here do have identical overshoot peaks. Like they're pretty close because the Routh-Locus shape is more or less preserved. The peak time is more or less preserved. The thing that's affected the most is transient response or the settling time because you want to get to within 2% of the final value, which takes forever with a PI system. Anyway, that is it. We'll continue this tomorrow. Thank you.